Hello, good afternoon everyone. My name is James Cleverley-Prance, and today I'll be talking to you about Kubernetes networking. So a little bit of background about myself. I used to be just a pen tester, but these days I sort of specialize in cloud native pen testing, sort of doing training and workshops, and also CTF events at Control Plane. So what are we going to talk about today? We'll look at the attack service of a Kubernetes cluster, what primitives of the cluster network we can abuse, and we will delve a little bit further into CNIs in two different parts, and then at the end we'll have a little bit of a look at how we can defend against some of the issues that we discuss. So why do we care about Kubernetes network security, or specifically the bits we're going to talk about today? Often in security audits, or if you ever do threat modeling, we look at the perspective of a cluster from a compromised pod. So this is maybe we assume compromise of a web application, so sort of an RCE vulnerability or something similar. We also sometimes assume a compromised insider. So this would be something along the lines of developer laptops compromised, some kubectl or a kubeconfig, credential file is compromised. Maybe it's committed to GitHub. But they're fairly well explored. And today we're going to look at clusters from an unauthenticated perspective. So if you're familiar with sort of Linux tooling, you might be familiar with Nmap. So the screenshot on screen is looking at a typical Kubernetes worker node. Typically you'd see these three ports. So hopefully you're all familiar with SSH. And the bottom two are starting to show us some of the attack surface of a Kubernetes cluster. So 10256 is a port used by the kube proxy component, if you're sort of running the stock kube proxy. And 10250 is the kubelet API. There is some attack surface to this port that we won't go into a massive amount of detail here, because in all modern versions of Kubernetes, it's authenticated, but there's a great tool from CyberArk called Kubelet-CTL that allows you to explore this in a bit more detail. And if we sort of hop on a node, we can just sort of verify that that's where those programs, are using those ports. So in this screenshot, we can see a port scan of a control plane node. It's a little bit more interesting, a few more ports here to look at. So we've got the familiar port 22 for SSH, and 10250 and 10256, as we discussed in the previous slide. But we also have three other ports here. We have 2379 and 2380. So these are for clusters that self-hosts etcd. So you won't see these, well, if you're in a managed offering, you wouldn't generally have a control plane node. But so for sort of a kubeadm style cluster, you'd expect to see some nodes with these external etcd ports listening. If they've been configured correctly, they'll be set up using MTLS for authentication. So there's not too much attack surface to investigate here. And the last port that we haven't talked about so far is 6443, which is for the API server. So being a good security, I guess citizen is the wrong word, but as a nod to as Kubernetes is mindful of security, I should say, the API server is served with HTTPS, as we might expect. But with that, the HTTPS port serves as a certificate. And so we can use, which has a lot of information encoded in it. This OpenSSL incantation will reveal some of that information. You could go to it in a browser and look the sort of a more graphical way of looking at the certificate information there. So this is the OpenSSL incantation to get some of the information out. So we'd expect to see here things like issuer, common name, and some other stuff which is not so interesting, but one of the more interesting bits here is the subject alternative name field. So the way that the API server is deployed and the TLS is constructed usually is that the API server listens on multiple IPs or IP addresses within the cluster and can be accessed via many or a few different service names. And in order for the HTTPS certificate to validate correctly, the subject alt name is filled out with these extra IP addresses and DNS names. So this is a really useful way for us to be able to find this information without being authenticated to the cluster at all. And we'll use this information a little bit later on to help inform some other attacks. Many of you may be familiar with the kubectl version command. What you might not know is that in many clusters, the /version API endpoint is actually unauthenticated. And so just with curl, as you can see here, you can directly make a request and get all this lovely information from your cluster. Admittedly, there's not an awful lot there, but it's from a user that has no access to the cluster whatsoever. They are able to build a picture of what version they're running and a few other bits. On the third line there, that Git version will often contain a provider string as well. Here, this is a kubeadm cluster, so it doesn't. But there might, in like a managed provider, you might have like a -GKE or something along those lines. So far we've looked at TCP ports, but something that's often overlooked is UDP. This may be partly because it's a little bit harder to scan for UDP, just because it's not connection-based protocol. But if we have an idea of the sort of protocols that we expect to be listening, we can conduct limited port scanning of UDP ports on our nodes or on machines that we expect to be nodes. So in the scan here, I've picked a handful of UDP ports that are known to be associated with technologies that are often used in Kubernetes. Specifically, so there's an NFS port there and a couple of other ports that are used for storage and networking. And we can see in this scan that we found port 4789 to be open. This is actually incredibly useful because it tells us that the cluster is using VXLAN overlay networking and allows us to start making a guess at not necessarily what the CNI is, but some of the technology that's in use by the cluster. So far, the issues we've discussed are probably informational if you were to find them in a security report or get them in a security tool. And it's all well and good, but on their own, not of too much concern. So in this next bit, we're going to look at things that are a little bit more significant. The underlying primitives of Kubernetes, or much of Kubernetes, is built primarily on Linux nodes. And for those of you that have deployed Kubernetes clusters using tools like kubeadm, you might be familiar with this sysctl. And this IP forward sysctl is an instruction to the Linux kernel that tells it to enable IP packet forwarding based on the IP tables configuration that it knows. And that's necessary for the IP forwarding within kubeproxy and within some of the other sort of core components of Kubernetes. However, this can pose unintended consequences. In the words of Rory McCune, this turns Kubernetes into a router and means we can forward or make use of this or an attacker can make use of this in ways that we may not want. So for this scenario, I'm going to ask you to envision an architecture like the one illustrated on screen. Imagine, if you will, that being good citizens and trying to secure our cluster, our security team has told us to take our API server endpoint off the internet because, for reasons that we discussed in the first section, it exposes information about our cluster and is generally best practice. As a result, because we still want our developers and our users to be able to access the cluster, we've implemented a Bastion host, pictured in the orange on the left. And we've deployed this Bastion host in the same subnet as all of our nodes. So we're in the same level 2 network as the nodes in our cluster. What we can do, due to the IP forward configuration, is actually route directly to those nodes, and which I will show you now in a bit of a demo. Right. He says if he can unfull screen. How's the size at the back? Can everyone read? Awesome. So we're going to start off by enumerating that basic information that we talked about right at the start. So I've got an nmark script here that kind of does all those steps in an more automated fashion. So we can pull DNS names from that certificate and some IP addresses of interest. We can see we're running in a fairly up-to-date cluster. And we get all that information from the certificate. So if we have a look at our routing table, that's what it is just sort of to start with. Now what we're going to do is, based on these IP addresses up here, make some educated guesses about the network ranges in use by our cluster. So we're going to guess that one of these, or well, not guess, we know to a certain extent that one of these IP addresses is in our service range in our cluster, and the other one is going to be on the physical network that the nodes are at. And because we're in that same physical network, we know that this one is the one in the physical network, and this one is a member of the service range. So we'll make an assumption that it's a /24 network and add a route to this via that node, like so. And we can see the route was added successfully on that second line. We're now going to look for a common service that's installed in Kubernetes, which is core DNS. Not every cluster uses it, but many of them do. We're going to perform port scan on TCP port 53 over that service range that we just added the route for. He says hopefully. Okay, it's not quite as intended. Sacrifice to the demo mod. Gods was obviously not made sufficiently. Bear with me 1 second. Slightly peeling back the curtain here so you can see what's running underneath the hood for this demo. I'm not 100% sure that didn't work, so I'm just going to try that again. If anyone wants to make a small sacrifice in the meantime, please do. Not quite sure why that isn't scanning, but we should, what we can do is, we know that we're able to, or should be able to find that the core DNS service is listening on a very specific IP address. And then what we'll do is use a DNS query using some legacy functionality in core DNS here that allows us to discover all of the services that within the Kubernetes cluster. This is just an example service that we're going to target because it's commonly available and it's just a good target for this demo. So I'm hoping this one will work. So for the rest of, so what we should be able to do here is directly list all the services in through core DNS. What this allows us to do is enumerate further information about the cluster, including the final third pod address range. Once we've done that, we can add a route to that range as well and directly talk to any of the services that are listening in the cluster. Obviously, this is not ideal, but it is the state in the default state in Kubernetes.
Could you scan it on UDP instead of TCP?
Possibly. I'm not sure that's what's caused it to break.
Can you repeat the question?
Oh, sorry. The question was, could you scan on UDP instead of TCP? Yes, you could. And the answer is yes, you could, but it's not why it's not working this time around. I'll have to get this working and come back to anyone interested after the session. Back to the slides. Says if you can get the slides working again. So this functionality is a little bit more commonplace than you actually might expect. It seems like functionality that, wait, why does this exist? Surely it should have been patched out a little while ago. But it turns out that the layer 2 routing is actually a feature of many CNIs that you might be familiar with. There used to be a Kubernetes mode called KubeNet, which essentially was this functionality. It's not really used these days. Other CNIs like Calico has a mode where you can route some stuff over layer 2 and some stuff over overlay. Some of the providers here, KubeRouter is just essentially just this. And K8s and GKE have legacy modes where you can enable this still, and if you're not careful in GKE, it's default, depending on how you instantiate the cluster. It's understandable why you would do this, because it has performance, complexity, benefits, just to name a couple. But it's a little bit scary if you don't know about it, I would argue. So moving on from layer 2 networks, there are many circumstances where that's not going to be your architecture. I imagine many of you will run your clusters with multiple subnets. And to do this, you would use overlay networks commonly. So there are two types of overlay network, which are VXLAN and IPIP, or two common ones that are using Kubernetes anyway. So for this next section, I'd like you to envisage this architecture. So where we'll have the bastion in one subnet, and our nodes are in one or more other subnets, but we can route traffic between them, crucially. So looking a little bit at IPIP, in terms of OSI model, the IPIP overlay network is a IP packet in an IP packet. So a normal packet will look something like this, whereby the outer packet is used to contain the node information, and the inner packet is used to contain the pod information. However, if we're using that scenario with the bastion host, then actually it's possible that we might be able to spoof traffic. So we need to keep the destination IPs the same in these packets. As we can see in the diagram, but or an attacker would have control over the source IP addresses. So for the inner IP packet, we would set it to, or we could set it to the bastion host IP address. And what this will allow us to do is make use of something called asymmetric routing, whereby the packet that goes to the node will be encapsulated, be routed according to the IP tables, rules on the node, and then because the IP address of the inner packet is set to the bastion, it will route back to us without being encapsulated. The source address of the outer can either be set to another node in the cluster or our bastion IP address, depending on which CNI we're using and some of the sort of spoofing protections that are available. So I don't know how readable this is, but I wrote a proof of concept in Scapy, which is used for a great library for writing, sort of doing low-level packet manipulation, which I have a link to at the end if you're interested. And we can see that we can make that similar DNS query and pull out all the services in the cluster. We can see the Wireshark dump here, whereby we make the standard query on the top line, and the line below it is our standard DNS response. Looking a little bit deeper, we can see the encapsulated packets going out and the unencapsulated packet coming back. And that shows us a successful DNS query from that bastion with absolutely zero authentication. You can do something very similar with VXLAN, but I'm going to skip over that in the interest of time. Back down to what we can do about this. So obviously this is not ideal, but yeah, there are a few things we can do. So you'll have noticed in the demo that I was the root user on the bastion in all of those scenarios. Theoretically, we don't even need this, but I used it freeze. If any of you know of the dev TCP pseudo device in Bash, you could likely use that to create raw packets. You can also solve this on an architectural level by just making sure any bastion hosts are located or sufficiently segregated away from your Kubernetes node pools. A kind of similar way of solving it would be that not to allow either IP traffic or VXLAN operates on a number of known ports. So if that traffic isn't allowed between your various subnets, then the attack would fail. All of the things I demoed today assume that no network policies are in place, especially some of the DNS stuff. Make sure that you have network policies, especially in kube system, so that because if you did and you could prevent DNS queries from outside the cluster into kube system. It's a bit obscure, but sort of yeah, it would prevent the attack. And then finally, IP spoofing protection, make sure that's turned on, and RP filter is a kernel mechanism to prevent the asymmetric routing, which you can turn to strict mode, but may break other things. So that's the end of my talk. The various proof of concepts are available in the links. And that's me on Twitter if you want to follow me.